All right. I think we've got everything on. I think we did it.
Great.
It's always hard to know. That's awesome. Well, all right. Welcome back to the Hurwitz Lab. I'm very excited to continue our physiology series today on the topic of potassium to complete our physiology trifecta.
Right.
You may recognize my guest, Dr. Alan Segal, who's college educated. Thanks for wearing the sweatshirt.
You're welcome.
He's a physician engineer. He's a nephrologist. He's a physiologist. He's an epitheliologist. And I'd like to remind you to check out Alan's previously guest appearances here on the Hurwitz Lab, where we discussed the topics of water balance. We discussed hyponatremia and also our discussion on metabolic acidosis. Right. Today, we really get to dig into Alan's wheelhouse while we talk about potassium. And as most of my friends know, I'm a positive guy. I'm excited, no pun intended, to discuss with Alan our favorite positive cation, kalium, also known as potassium. Potassium that is so beautifully responsible for essentially every excitable cell function and regulated meticulously by the kidney. Alan, welcome back to the Hurwitz Lab for your third podcast in our series.
Well, thanks, Craig. This is fantastic, actually. I mean, as much as I love salt and water that we did the first time, and I love acid base, potassium is very close to our kidneys.
That's true.
And it's also very exciting because in terms of work we've done together, I mean, we've discussed, academically salt and water and acid base, but our actual research and work was devoted to potassium homeostasis and ion channels, including potassium channels that you recorded from. And I'm happy that we're going to be showing some of those today.
That is awesome. It's going to be a real fun review for me to see that old data.
Good. Great.
Nice. So you want me to bring up the slides? Let's get into this discussion.
Perfect.
Excellent.
Okay. And I got the mouse now?
You do. Oh, slide it over right to the middle there. It'll come in. Let me get it for you.
There, I got it. Yeah. Okay, great. So we are talking about potassium homeostasis today, and I've subtitled the talk Lions and Zebras and K, oh my, based a little bit on The Wizard of Oz. And I hope will see why it's titled that. So some fun facts to start off, because just to set the stage. So as Craig mentioned, potassium is the dominant intracellular cation. And potassium content of the typical, what they say, 70 kilogram man is about 4,000 millimoles total. And the amazing thing is that all of that 4,000, except for about 56, is inside the cells. So only 1.4% of the potassium is outside the cells. And the intracellular potassium concentration, depending on who you read, is anywhere between 140 and 150 millimolar. And the extracellular potassium has a range of 3.5 to 5, but we're going to call 4 millimole the normal, and you'll see why in a second. So mammalian tissue, if you just look at heterogeneous mammalian tissue, is about 57 millimoles of K per kilogram of tissue. So if you think about a newborn baby, let's say a baby is 8.8 pounds, that's going to be a total body potassium of about 228 millimoles. And how does the baby get all that potassium in its cells? Because each time the cells divide, they have to have the potassium. And really, the mother doesn't have to do much. Since there's 270 days of pregnancy, you really only need an extra millimole of extra potassium per day for the baby, and that's essentially 1 inch of a banana.
That's interesting. Right, exactly.
It's 1 inch of banana. Now, the reason the kidney is so important in this is because for every 100 millimoles of potassium we eat, the kidney is going to get rid of 92% of it to keep us in steady state, and the colon is going to get rid of the other 8%. And the other amazing thing about potassium disposal is that all of it happens beyond the loop of Henle. And so that's where the real tight regulation is, in that tight epithelium, and it's beautifully coordinated. We'll go over that. And one thing that's been a hot topic lately with potassium that certainly wasn't around.
I know I'm going to learn some new stuff this time.
So one interesting part of this, which I'm not going to go into detail, but I do want to make sure I mention, is that there's been some elegant work that shows the circadian and diurnal rhythm of potassium homeostasis. Everything is on biological clocks, and potassium homeostasis is no exception. So that's very interesting, actually. Now, we get all of our potassium to eat. We have to eat it. And foods that are high in K include vegetables and fruits, and I already mentioned the banana. And then, there's a chapter that I wrote on potassium in 2013, which if anybody wants to read that, it'll put you to sleep for many nights because it's a very long chapter. But one of the things
it's much better to listen to the podcast.
I think so. But one kind of case that I saw when I was researching that chapter is something that I didn't know before, which is cautopyrophagia. And like all these things that end in phagia, it's a dietary pica. But this is where a person has a craving to eat burnt match heads, not match heads.
Interesting.
Burnt match heads. So they not when they're hot.
Right.
So
not when they're cold.
And not when they're cold. But
pre-burnt.
Right. But there was at least one case in the literature where a dialysis patient did this. And, they depend on dialysis for potassium removal. And he presented with severe hyperkalemia because he was eating match heads.
Right.
So that's amazing. Now, the thing I want to focus on first is that recent data, have suggested that higher potassium diets are actually healthier for you, especially from a cardiovascular point of view. And we've known for some time that people that have a higher potassium diet tend to have lower blood pressure, and they tend to have less sticky platelets. So that may be very important for our cardiovascular health.
Hey, did you miss the sign that says "shut all cell phones off" when we start the podcast?
I might have missed that.
Well, I think I'm going to have to check mine too.
No, I might have missed that. But in this respect of the diet, what was very convenient because of our schedule. This is just a little picture of the higher potassium foods, and really, if you have healthy kidneys, you can eat. I mean, the cave people, turned out it was easier to eat plants than because they didn't run.
Right.
And so cave people were eating a diet of up to 400 millimoles of potassium a day. And most of us, it's 80 to 120. So this was a huge potassium load. And so the kidneys got great potassium excretory capacity.
And I think of it, as you're talking, this is making me think that what you're talking about right now is really our external management, how much comes in and what goes out, the mass balance, and then the internal regulation, which happens at this finer segment of it.
Right.
But
and we're going to get into that
into detail.
Into detail. But this is just for people that wonder. So this is a very good, the foods on this slide are very good if you have good kidneys and keep you healthy. On the other hand, if you're a dialysis patient, we give this same sheet to the dialysis patients of foods to avoid.
Right.
So it's definitely a two-way street.
And it's unfortunate because these foods are so healthy for you.
Exactly.
And that is one of the big dilemmas we run into when you have to limit diets of things that are really important for vascular health.
Well, fortunately, because of new binders, much newer than K-exolate,
right,
we've got some great new drugs that are making life a lot easier for our patients.
True.
And I'll get into that as well.
That's awesome.
Oh, good. So it just so happens, Craig, that after we scheduled this session, last weekend, the New England Journal Online came out with an article that everybody's looking at this week. And this is the article, 24-hour urine sodium potassium excretion and how it relates to cardiovascular risk. And this is just from last weekend.
That's amazing.
Yeah. And so here's the basic findings of this paper. And everything is here. If you look, the Y scale here is the hazard ratio of doing badly or dying. And what you see here is very easy to interpret. The left upper shows that the more sodium is excreted, meaning the more sodium the person ate, the worse they do. On the other hand, the upper right shows the more potassium they excrete, the better they do. And then the combination of those two is the lower panel that shows the ratio of sodium plus sodium divided by potassium excretion. And you see when the sodium to potassium excretion is high, so is the hazard. So all of these data, and this is a very good study. It was done very well because to get into the New England Journal, you have to do things quite carefully. So the paper spends a lot of time on methods.
Oh yeah.
And so this is very important. And I think again we have to modify this slightly maybe for our advanced kidney disease patients, but for the general population, this tells us something. And it says eat potassium and less salt,
That's
less
true.
sodium.
Mm-hmm. And this could also be why, look what happens to our kidney patients. They can't excrete potassium.
Right.
Is that part of the process that puts them into this high risk?
Well, and we'll talk about maybe at a future podcast why having kidney failure is not good for you.
Totally. That is coming up next.
Yeah, but I'll tell you for sure, the kidneys keep you alive in more ways than people may think.
That is for sure.
And when you lose kidneys, you lose more than the kidney function.
You lose the aging, the protection from aging.
You lose the protection from aging. You lose the brake on the cardiovascular system.
Totally.
I mean, I hate to say it because I have a lot of friends who are cardiologists, but we've known for some time that the heart is trying to kill us. And the kidneys
keep saving us.
The kidney keeps saving us, exactly. And we'll talk about that at one point.
But that's an interesting paper that just came out. That's awesome.
Yeah, it's just last weekend and just in time for Thanksgiving. So you can modify your Thanksgiving plans. I want a high K turkey.
Yeah.
So now here, as we said when we first started talking about steady state, Goldilocks always told us, you know, you don't want too much, you don't want too little, you want just right. And so every time we look at these physiology curves, we see the U-shaped curve that says there is an optimum. And for potassium, serum potassium level, plasma potassium level, it's between 4 and 4.5 millimolar. And again, there's mortality that goes up on both sides of that. So there is, you know, just like we saw that the optimal sodium concentration was 141, the optimal potassium concentration is 4 to 4.5. Mm-hmm. And so that really is a very important slide to keep in mind. Now, I wanted to relate my first case on call when I became a fellow. I remember this very distinctly. It was my first night on call as a fellow at Yale, and the emergency department called me about a 21-year-old female college student, and they told me her chief complaint was she can't move. And I said, oh, there's only a couple letters difference from nephrology and neurology, but I'm not neurology. And they said, no, we know you're nephrology. And I go, ooh, she can't move, and you know I'm nephrology.
Right.
So what's going on? So as it turns out, you know, I at first asked, you know, is there any family history of everything like this? And has she got any genetic reason not to move? And the answer was no. So they told me about her exam. She was, you know, normal size, 60 kilograms. I had a normal blood pressure, a normal heart rate, and she is normal volume status. She did have some poor dentition, but she was very weak. She was very weak. The muscles were weak, and the nerves and reflexes were not normal. So they cut to the chase, and they told me, we're calling you because her potassium is below 2. Her extracellular potassium concentration is below 2, and her kidney function is normal. So why can't she move? So the first question I want to talk about and introduce the topic is, why can't she move? And obviously it's got to do with the potassium, but why? So here's our guy. Here's one of our guys.
One of our guys. He's right up there with Henderson and Hasselbalch.
He is. And, you know, as I might have mentioned before, Walther Nernst was the first person to win a Nobel Prize in our field of electrophysiology. And since he won the Nobel Prize in 1920, there have been 5 other Nobel Prize, not winners, more than that, but 5 more Nobel Prizes awarded for work in electrophysiology and ion channels, including this year with the TRIP channels and the piezo-1 channels. Mm-hmm. So, and we're lucky to know those people. Anyway, Walther Nernst, who did get the Nobel Prize in chemistry, developed an equation in 1888 that was the first time that people could that he related the chemical gradient to an electrical potential. So this is the classic electrochemical gradient we all learned about in high school and college. And what Nernst said is, if you take the ratio of a cation on the outside to the cation on the inside, you take the natural log of that, and you multiply by 25.4, which is essentially the number you get when you have Faraday's constant and the gas constant and temperature. Basically, that gives you the driving force or the reversal potential for that cation. If you do it for sodium, since there's 140 on the outside and 14 on the inside of the cell, you get positive 58.5 millivolts. And if you do it for potassium, because the ratio is in the other direction, biionic potential, you get minus 90. This sets up life.
This is the stage.
This is the stage, because driving forces are hard to establish, and you can't change them quickly. So you really want them to be set, and then, you know, a little trickle battery to keep them that way, sodium pump. But really your ion channels are going to regulate the permeability from moment to moment. So let's take a look at that. So the reason she can't move is because of her low potassium level, she's moved where Nernst potential for potassium is. And so you see what happens. Here's just how an action potential forms. We've seen this slide before. And it involves the activation and inactivation of voltage-gated sodium and potassium channels. So because at rest, most cells are dominated by their potassium channel conductance. the cell membrane potential of -70 is very close to the -90 reversal potential for potassium.
It's that resting membrane potential.
Resting membrane potential reflects what is the dominant conductance.
Yeah.
And as you know from your recordings, we're going to get to that, you know those are potassium channels.
Yeah.
But what happens is sitting and waiting in the membrane are all these voltage-gated sodium channels, and there's a zillion of them, but they're just all closed. So when neurotransmitter leaks over and causes their small depolarizations, you'll reach a threshold. And when you reach that threshold, those sodium channels, bang, they open. And when they open, they dominate the conductance. They dominate the conductance, and the membrane potential shoots up toward ENA, just like you're seeing it on this slide, okay? And then as soon as it opens, the beauty, they close. And so you get this bang, and open, close, so you get a spike. And in fact, the potassium channels also open a little bit later, and there's more channels open than at rest. So actually, when the sodium channels close, you hyperpolarize the membrane potential, and then you come back.
Right.
But neuromuscular transmission, excitation, and coupling of impulses to muscle, electromechanical, electrocontraction. When you fool with a Nernst potential, the old commercial, don't fool with Mother Nature.
Right.
You can't fool with EK, because if you do, you're not going to be able to move.
Right.
And that's why she can't move. And again, our equation at the bottom, flow is transport is driving force times permeability. And this slide tells it all. The driving forces are set by the Nernst potentials, and then the channels control where you are at any given moment. And again, potassium channels, they were probably among the first channels ever. And there's more than 1,000 superfamilies of potassium channels, because nature plays variations on this theme and keeps building. It's always let me have a K channel and let me make some changes to it.
And in any cell we're working in, whatever the function is, let's figure out how to use this powerful tool.
Exactly. So it's give me the channel with cheese, give me some mustard on
Yeah,
that,
right.
and they're all different. So let's talk about, in her particular case, she's got hypokalemia. So since you have to eat the potassium, and the kidney excretes the potassium, what are the ways hypokalemia can develop? And one way they can develop is if too much of the potassium is taken out of the extracellular fluid and goes into the intracellular fluid. Now, normally, we have two big hormones that help us do that, insulin and epinephrine. But if somebody's got a tumor that secretes insulin, that's one example of somebody who will be very hypokalemic. Now, does she have that? And the answer is no, because she's got a normal glucose. Okay. Now, beta-2 agonists like epinephrine, albuterol, or if she had a pheochromocytoma, could also produce this kind of hypokalemia from just transferring.
Right.
And she's young, feels extraordinarily rare, and she's too young to have it. And there's no exposure to epi or albuterol, and she's not shaking like somebody who's over epiized. Right. So it's not like it's finals and she's all hyped up.
And these are all things that rev up the sodium potassium ATPase, so that they're just shifting potassium into the cell.
Yeah, really the only way into the cell, for the most part, is everything's going in by stimulating the pump.
Right.
And the pump, of course, was the first gut kidney. It eats potassium and excretes sodium.
Right.
So the fact that she has a normal pulse and blood pressure suggests that's not going on. Could she have hypokalemic periodic paralysis? Well, that's a genetic defect where a family history would be there. She doesn't have that. And then you're looking at some really rare things like barium intoxication. We use barium in our patch pipettes to block the potassium channels, and this blocks efflux of K from the cells, and so you get hypokalemia. None of these are what's going on. Okay, so we're going to have to see. So we can't fully exclude the barium, but
it's always in the history.
It's always in the history. But let's take a look what could be going on. So this now brings us back to the beginning. I wanted to start off with that and come back to the beginning. In the beginning, again, you have all this sodium on the outside supporting life itself existing in the cell where the potassium is. And if you buy biochemicals, when we were in the lab together and bought biochemicals, we noticed they always came in potassium salts because nucleic acids and proteins, they live with potassium. They don't like sodium. Okay, and so then there was this membrane, and on the membrane are the channels. And so there we are. We got the high potassium kaline on the inside and the high sodium saline on the outside, and there's our pump and there's our channels. Okay, so here's just the overview again from, I love this figure because it's from Gerhard. Gerhard was a longtime friend of mine one of the pioneers of kidney physiology, including potassium. He's really probably written more papers on potassium channels in the kidney than anybody. He was at Yale. He lived to be 93 or 94, passed away a year ago, April.
Wow.
But I still love this figure from a 1998 review he wrote. And again, it makes the point. This is the cell with 98% of the K in it, and the outside has only 2% or less than 2%. And then you got this pump and channel that are doing that. And here's your input, simple input-output. Here's your input of 100% of the K, and the kidney is excreting 92% of it. So hypokalemia is usually due to either a GI loss of potassium like diarrhea or a kidney loss of potassium, as happens in diuretics. And again, people have to remember that when a person vomits, the hypokalemia that comes from the vomiting is mediated by K loss at the kidney. So
Right.
even though the vomiting
Because
is your gut.
it's driven by chloride and proton loss.
Exactly.
It's the electrochemical changes.
Exactly.
All of our talks, water balance, proton balance, now potassium, this is the closer. This is how we put it all together. It's right in the middle.
Yeah, and that's what I'm saying. These concepts come up. On the other hand, hyperkalemia, if you look at the slide, hyperkalemia has got to be easy too. I mean, it's either something's getting in the way of the kidney doing what it wants to do because it has that huge capacity. And the things that get in the way, I mean, back in cave people day, they could eat all that 400 because back then, first of all, there probably wasn't a whole lot of ACE inhibitors or ARBs or mineral corticoid receptor
I was going to say, there
blockers.
were no doctors back then giving them
very
spironolactone.
There were very few doctors, and so right. So there was that going on. So
We
they
need to show that slide.
Yeah, so they didn't have a lot of these meds, and these meds all interfere. These are great medicines for blood pressure,
Oh.
and now we have new uses for aldosterone antagonists like finerenone. These are very important medicines, but they are one of the costs of using them is that they decrease the disposal of potassium by the kidney. And that's why patients with kidney disease, we always have to say, we want you to be on an ACE inhibitor or an ARB for, to slow down kidney disease and for your blood pressure. On the other hand, hyperkalemia sometimes limits that, and that's why things like Lokelma and Patiramir that bind K in the gut can help us keep these people on these medicines. But anyway, hyperkalemia, you're usually looking at the kidney, and we'll get into the details of that. So one thing we wonder about is, I like to start with this because this is a very great question. Here it is in the wild. These lions, they don't have pharmacies, and they're eating whatever they want. Why doesn't this, and the female lion does the hunting. So here's a picture of a female lion who's hugging dinner, this poor zebra. Now, this female lion's 126 kilograms, and you can make the calculation that her total ECFK is 84 millimoles. Now, these lions, when they catch the zebras, they're hungry. They're not going to be eating it slowly. They're going to be eating it fast. And if the lion eats just 6.5 pounds of that zebra, which is nothing for a lion, that's already enough potassium that if the potassium stayed in the ECF, the serum potassium would go up to 12.1, and the lion would die of hyperkalemia. And again, the reason for that is shown here. Hyperkalemia is very dangerous for the heart because it changes the Nernst potential, and again, the heart is very sensitive to where that Nernst potential is. And it can fool you. EKGs are not reliable. And I wanted to bring
They are if you're a machine learning device.
Well,
they're not reliable if it's a doctor looking at one EKG.
Well, this would be a good case then, Craig, for your hypothesis. And the reason is here's 2 EKGs from the same patient that I saw. Okay, this was one of our patients. This patient happened to have something called tumor lysis syndrome. Okay, now here's an EKG on this patient when the potassium was abnormal at 6.2, and it doesn't look that terrible on the top. However, about a half an hour later, or less than an hour later, the potassium was 7.2, only 1 millimole higher. Yeah. But it made all the difference because you've got sine waves. So now what you're telling me,
that 1 millimole.
Yeah, what you're telling me is that the machine learning, the deep learning, is going to have been able to make these measurements. That would be great.
That would be great, but it didn't tell you what was going on because this patient was not in a steady state.
Right.
Key.
But an EKG is always a snapshot.
It's always a snapshot.
Okay. But anyway, this slide makes 2 points. One, the top 6.2, he would have been within his rights to have an abnormal EKG with peak T waves. He didn't really. And then, but 1 millimole later, and he went to the entire end of the other spectrum with the sine wave. Okay, so that's why hyperkalemia kills you, because of what it does to the heart.
Especially if you're someone who's never seen hyperkalemia before.
Great point. This patient, who is not a dialysis patient, who doesn't have chronic hyperkalemia, this is a person who's got tumor lysis. Normal.
Kaboom.
Kaboom. Exactly.
Right.
And now these membranes are not used to.
Not prepared.
And that's what, and I think that goes a long way to explain this.
And it's one of those reasons, a pearl you want to take away when you have those situations of tumor lysis syndrome or rhabdo. With potassium of 6.2, when you're not in a steady state and something's happened to someone whose normal potassium is 3, 8, or 4.
Right. And you
be
don't
on
know,
the lookout.
And you don't know where you're going to be a minute later.
You got it.
So why doesn't the lion die of hyperkalemia is the question we're trying to answer. And here's why. So first of all, the lion's at rest.
He's on Veltassa.
Yeah, well, he could be, but not this one.
No.
Now, when the lion's resting, the lion's hungry, a little bit maybe on the ECF volume depleted side, but the hormones you got to look at. The insulin is down because he's in the fasted state. She's in the fasted state. The epinephrine level is down because they're resting, and the aldosterone level may be up from a little bit of volume depletion. Now, then the lion sees the zebra and chases the zebra. Insulin is still low, but epinephrine levels are revved up. And again, the aldosterone still may be revved up. Now, it catches the zebra. Now, when it eats the zebra, the intake of the potassium and the carbohydrates are going to stimulate insulin. And the epinephrine level is still up from the chase. Aldosterone is still up. All of those are moving to do what's called the internal-external balance for potassium. So the insulin and the epinephrine, and to some extent, some people believe the aldosterone, are all promoting the transfer of stimulating the pump and bringing the potassium into the cells very quickly. And it's a storage area. Put it here. Like if you have a
it's the buffer system.
Yeah.
And I mean, but it is amazing how all these things are tied together.
It is in the sense a buffer. It's like, let's say you have a small apartment that's, if something's out of place, it's going to look pretty messy. And let's say you got this gigantic room of Fibber McGee's closet where everything is a mess. If there's any mess in the little studio, you throw it into the big closet of mess. Nobody notices that.
Right. And
the studio looks great again.
Right.
And then when you get a chance, and this is the kidney now is going to excrete that. Now when you trained, and certainly when I trained, but when you trained, we only taught you one way that the external control occurred, and that was that the aldosterone, by binding to the mineralocorticoid receptor in the distal nephron, what's called the aldosterone-sensitive distal nephron, would promote the disposal of the potassium. That's a feedback mechanism based on aldosterone. What we didn't know back then, and it was come out in the last, I would say 5-6 years, is now this new pathway of a feed-forward pathway, where actually, and I'll show you some of these experiments, once potassium gets into the stomach tells the kidney in a way we still don't completely understand. It tells the kidney, hey, I got a lot of potassium coming in here. Start doing it.
The stomach is amazing in how it measures things, even insulin. I mean, these things are regulated.
Exactly.
Even before, probably even when we're looking at the food.
Right. And so to cut to the chase of where that's going, when potassium hits the stomach, basically a signal is sent out to the kidney that has the same effect as a thiazide. What a thiazide will do, so when the thiazide-sensitive cotransporter is phosphorylated, sodium and chloride get reabsorbed. When it's dephosphorylated, it's in the inactive state. I will show you data later. When you feed potassium to animals, you can see just when the potassium hits the stomach, the dephosphorylation of the thiazide-sensitive cotransporter, and that's a potent stimulus both for the natriuresis and for the caluresis in the collecting duct. So you get natriuresis in the DCT, and then you get caluresis in the collecting duct. And so the body, again, perfectly primed because this was going on a long time ago. Lions were doing this. So here's my figure from, and this is a little bit of a complicated figure, but it's actually my favorite figure. I don't say that because I drew it. Well, maybe, but it's my favorite figure. And the reason is I think it really encapsulates everything. So what's in the orangey color here is the intracellular fluid. And then what's blue is the extracellular fluid. So here's potassium coming in through your gut. That's 100% of your daily potassium load. And here's, of course, the Gerhard. Kidney is going to get rid of 92%. The gut's going to get rid of 8%. And I stuck a mineralocorticoid receptor on here to remind you that that's stimulating that. Both the colon and the kidney have the mineralocorticoid receptor. Now, here what you've got is when the K gets eaten, what brings it into the cells really fast for the lion? And what brings it into the cells really fast are the insulin stimulating the pump, the beta adrenergics through cyclic AMP stimulating the pump. This one's through tyrosine kinase. What's going the other way is alpha adrenergic receptor. So again, in the usual fashion of alpha and beta being the flip side, the two things that bring in the potassium in are hormones working through tyrosine kinase and protein kinase A stimulating the pump. And then, of course, there's channels. So on this side of the slide, it's showing you what can change the efflux and influx of potassium. So one of the things that can affect potassium efflux is hypertonicity. Again, I mentioned alpha adrenergic agents and perhaps acidosis. Certainly inorganic acidosis does. Organic acidosis, no. So the hyperkalemia that we see in DKA is not due to the acidosis. It's due to the insulinopenia. Right. So the DKA problem's here, okay? Not here. And then the influx of potassium, of course, we mentioned insulin beta agonists. And so I like this slide because in a pinch, this is the slide you look at that's going to tell you everything about what's going on with potassium homeostasis. What's not on the slide, because it wasn't known yet in 2013, is the feed-forward pathway. So again, I would make another arrow now to say as soon as I have to draw a little stomach here, and then tell the stomach that it's a thiazide. The K in the stomach's like you ate a thiazide. Isn't that fantastic?
That's amazing.
And did you know? I mean,
I can't wait to see that.
But did you? How? I mean,
no, that
how
was,
aware? I mean, I
was not aware.
Yeah,
of that.
it's not. It's something that's out there. So to review for a second, we got our transfer to go insulin and epinephrine, bring it into the cell. We have the feedback system in the colon and kidney involving aldosterone, and then we have this new feed forward gut and what's called the kidney caluritic signal. It's something that the stomach knows, you know. I mean, they say, the way to a man's heart is through his stomach. Well, I don't know about that, but the way my thiazide-sensitive co-transporter is through the stomach. And so these are the three real things that are involved in K homeostasis. And now here's the detail of the kidney. And the bottom line of this complicated slide is this, that potassium handling along the kidney, nothing happens of importance in terms of the homeostasis until the distal nephron. So all the potassium that's filtered at the glomerulus, once you're through the proximal tubule and the loop of Henle, Berliner showed in the late 50s that 90% at least of that potassium has been reabsorbed.
Right.
And so even if you're hyperkalemic, you'll reabsorb all that potassium because that's not regulated. The regulated part is all coming next. Most dietary K. In fact, if you eat 130 millimoles of K today, 130 millimoles of K is going to come out pretty much 92% of it, at least, in your kidney, and all of it starting after the loop. Okay, so this now brings us to something that you've seen this a long time. You can tell by the color scheme that Craig was involved with the slide, because our favorite colors are here with the yellow lettering.
Yeah.
And so what's shown here is our proximal tubule cells.
And it's a beautiful cell. And I think I always, whenever I give a talk to the dialysis nurses, I always show them that slide with that cell with a nurse's hat on it.
Exactly.
And I say, if you want to know your job description, it's what these cells do. Look at this cell. Do you think it's one cell or two cells?
Exactly.
You taught me this.
So this is
beautiful.
This is a very unique cell.
This was your special prep.
Yeah, it was. It was our special prep. And these are special in the sense, and we wrote papers on this, when you dissociate cells from mammalian kidney, they will lose their epithelial polarity. And the amazing thing about these cells from salamander, amphibian, is these cells retain their polarity not just for a day or two, but for the Hanukkah miracle.
That's right.
For a good 8 days, And what you see here is the apical membrane, which has got, it seems like there's a belt here separating this into a kind of a strange figure 8 with this brush border. So you can clearly see the brush border is very lush, but abruptly stops at this cytoskeletal band. And then this is the basolateral membrane with the nucleus and everything, but it's one cell, and it retains what used to be on the urine side, and we've patched both sides of this cell. And we know from patching and looking at the channels on both sides of these cells, they're two separate populations of channels. There's K channels on both membranes, but they're different, okay,
Right.
different channels. And so we were patch clamping these cells, and in fact, we even did experiments where we would use two patch pipettes. We would use a regular pipette on the basolateral membrane and a macro pipette. I think we were among the first to do this. Certainly the first to do it in kidney, and recorded from this. So let's take a look. So here's from a couple of Journal of General Physiology papers based on the work that I did before I even moved to Vermont, came to Yale. Shows the basolateral membrane ATP-sensitive potassium channel. It's an inward rectifier. You see that because the channels, these few picoamps of channels, inward current is bigger than outward current at the same voltage. And here you see that there's a lot of current, but if you add nucleotides like ATP, the current goes away. But it's reversible. So this channel is present, and in macro patches you'll see current. Appreciable current, but all the current is turned off by ATP. So the channel itself, and ATP-sensitive potassium channels are very important in the pancreas, where they regulate insulin secretion, and that's why sulfonylureal receptors are used clinically, because the depolarization in a beta cell causes insulin to be secreted. So the sulfonylureal receptor blocker makes that channel close, the cell depolarizes, and maybe insulin comes out. So this channel, it shows you that channel is paying attention to intracellular energetics, okay? And it's very sensitive to the ratio of ATP and ADP. And we showed that here. We played around with a bunch of nucleotides. Here's data from a rabbit. The amphibian, there was nothing we ever found in the mammal that wasn't in the amphibian. This happens to show that again, here's a kind of a macro patch from rabbit proximal tubular basolateral membrane that had at least 24 channels in it that we could see. And again, when you add the ATP, it all shuts off reversibly. So these channels are, and this, at least in amphibian, this channel dominates 85% of this whole cell conductance. Here's your data. Again, you can tell by the color scheme. And this is a macro patch where we were using a sulfonylurea called glibenclamide, which is clinically used. It's glyburide. And you'd have to remind me of the trade name for it, because I only know the generics.
Right.
But what you see here on the left is that when we have glibenclamide in the patch pipette and time goes on, big inwardly rectifying. You see the inward rectifier here. You see this is the IV plot. Basically, this ramp shows you a lot of inward current and then no outward current, very little outward current. So this is our inwardly rectifying IV plot. But as time goes on, the channels are inhibited by the glibenclamide getting into the patch. And that was very nice. So when we excised the patch, the glibenclamide sensitivity seemed to go away. Something got lost. But the channels are still ATP sensitive, and here you see it. Here's an excised patch doing fine, but when we add ATP, the channels go away. So at least the currents go away. So this was and the benefit of having macro patch is being able to see the whole ensemble of channel activity. Single channel recordings are fantastic, but you really want to see what the chorus looks like.
Exactly.
You got your soloists,
yes,
but you want to see the chorus. Now, here's the old nephron again, and we got the body on the blood side and the outside world on the urine side. And we're really focusing today on, the distal nephron. So here again is the loop of Henle, where the loop diuretics work. And this is not, loop diuretics do not give you hypokalemia because they block this. Loop diuretics gives you hypokalemia because a lot of sodium is passed down to the distal nephron.
Right.
And that's where it's happening. And that again is here. Here's the thiazide-sensitive co-transporter. This is the one that's active when it's phosphorylated and dephosphorylated by eating potassium. And because, I'm on chlorthalidone, which is a very potent inhibitor, long-lasting inhibitor of this. And chlorthalidone is well known to, and again, I have to be careful. I have to eat a high potassium diet because my chlorthalidone for my blood pressure and my kidney stones is great. But if it lowers my potassium levels in my blood, and that's not healthy,
right,
I don't want that. So I have to eat a high K diet because I'm not on chlorthalidone for a potassium problem. That's just what I'm getting. And then, of course, can we go back? Is he able to go back?
Yeah.
Okay. See if we can go back. Yeah. So, yeah. Well, I guess I must have forgotten. We'll get to the collecting that must be coming up. Anyway, one of the other things we mentioned, there's been this paradox that people have wondered about for years about aldosterone, because aldosterone seems to the two main stimuli for aldosterone are ECF volume depletion,
Right, volume depletion,
which is a loss of total body sodium, and the other major activator of aldosterone is hyperkalemia. So, so the question was, what if you got both problems? If your potassium is fine and your volume depleted, then aldosterone's great, helps you restore volume, but you wouldn't want that to make your potassium go low.
Right.
On the other hand, if your volume is perfect and you're hyperkalemic, like the lion, you don't want the aldosterone
to raise your volume.
Right.
So
this was called the aldosterone paradox, because it's how does the body know whether, since aldosterone's got two arrows.
Just look in the book of why.
Look in the book of why. So aldosterone's got the two arrows of what's stimulating it from the zona glomerulosa, but how does the body know which one's which? So there's what I wanted to introduce that. I wanted to show you that what gets the aldosterone, just like insulin is stimulated by membrane depolarization of the beta cell, aldosterone is another hormone. It's stimulated by depolarization of the cells of the zona glomerulosa, which is the outer layer of the adrenal cortex. So when the lion eats and the ECFK goes up, aldosterone is stimulated. Even if it was already a little stimulated from the volume depletion, it's stimulated big time, pedal to the metal
for K management
from the depolarization of the zona glomerulosa cell. So that's what's shown here, and those are the cells. And this is the adrenal is involved, and that's why when people develop adrenal adenomas secreting aldosterone, they're going to get hyperaldosterone problems. So here's the aldosterone paradox that I talked about, and how do we resolve it? So on the left, you see hypovolemia, and it stimulates aldosterone, but notice it stimulates aldosterone via the angiotensin II pathway. So whereas hyperkalemia skips over that. So on the right, when the ECFK goes up, you get hyperkalemia and aldo without the intermediate of the Ang2. And so this turns out to be probably an oversimplified way to look at it, but it turns out to be the answer. The balance between how much of the aldo is aimed at volume restoration and how much of the aldo is aimed at K disposal is sort of balanced by how much Ang2 is in the mix. And so that's the answer to the aldosterone paradox to some extent. Okay?
That is interesting.
And it's a fine point. I don't know that they're going to put this on anybody's medicine board.
No, but it's super interesting to separate, because I never really have thought of it that way, that aldosterone had this targeted management of these. I always think of them together, and we always do, because we think of hyperaldo.
Yeah.
Like when it's when it's not when it's primary,
uncontrolled,
when it's not secondary. Yeah. I mean, this is secondary hyperaldo.
Yeah.
Because you have some other reason you got a stimulus as opposed to primary, where it's doing probably both of these things. But that would be interesting. Do you ever get hyperaldo where it only goes down one of these pathways?
I think if you got hyper Ang2, it might.
Right.
But no, but this bothered physiologists for a long time. I mean, one of the reasons my fellowship took 4 years was because at Yale we weren't allowed to. We would say, "When's the fellowship over?" And they said, "Well, there's 2 ways your fellowship can be over without you dying."
Right.
And I said, "Well, what are the 2 ways?" They said, "Well, the first way is you get an NIH grant," and they said, "But the harder way is to figure out the aldosterone paradox."
I love it.
So
that's super interesting.
And so this is great work that's also fairly recent. This is a paper actually that's only in the last 10 years or so.
Yep.
So here's our old picture of the collecting to cut open on our old 2 cells, the principal cell, and which is really the one that's doing the big work in hyperkalemia. But the intercalated cell might have the maxi K channel in it as well, and so therefore that's a flow activated channel, and that will also help. So here's classic work, and again, I love one of the things that's great about doing these talks with you, Craig, is because we have we can relax enough to really go back to the historical fundamentals, because a lot of people who are potassium, even experts today, well, I wouldn't say experts because they probably do know this, but people who know a lot about potassium may not know the fundamental cornerstone. There was a time this wasn't known.
Right.
There was a time where people didn't believe the kidney had the ability to secrete anything. What proved it was finally in the 50s and early 60s in work that was done by Gerhard. What they did with micropuncture is they took distal nephron. What you see here, the x-axis here is how far you are along the distal nephron, from the early distal nephron to the late distal nephron collecting duct. And what they showed in a beautiful paper, and you can tell it was a beautiful paper because, what was it, American Journal of Medicine. And this beautiful paper, which is now in every historical kidney book, but Homer Smith's time, they didn't know this yet. This was published in 1964, does it say? 1964.
64.
So in 1964, what Gerhard saw was as he went along the collecting duct, the distal nephron, and measured sodium, it was disappearing. At the same time sodium was disappearing, potassium was appearing. Now, what they thought, and I was taught this, so this comes out in 64. I'm in med school in 84. 20 years ago by, and we were taught that there's just this exchange mechanism.
Right.
It was a simple exchange mechanism. So sodium goes in, potassium goes out of the earth. And there are still board review books that say that. And one way I check how good a board review book is I just turn to the page. This is the only page I need to see. If they are saying that, you can throw the book away. Okay. So what we now know is the reason that sodium was disappearing was it was being reabsorbed by ENaC. And yes, those things are coupled because
there is an exchange, but it's not an exchanger.
Not an exchanger. It's two separate channels.
Correct.
And so you explain how it is that the reabsorption of sodium through ENaC promotes the secretion of potassium through ROM K. Explain that.
Yeah, no, as the cell gets more positive on the inside, the cations are driven out through ROM K.
Driving force. So the permeability is there,
right.
And now the driving force is being tweaked a little bit. Leave it to the kidney to come up with that one.
That is beautiful.
So here's now where we see these two cells show up. Here's our nephron with, again, here's the ENaC. This is why the sodium was disappearing, and this is under the control of aldosterone through the mineralocorticoid receptor.
And I love when these ion channels they have their arrows in a direction, but the reason it's going in that direction is because of driving forces.
Absolutely. The electrochemical driving force is the reason for when the channel opens, the electrochemical driving force is what's going to...
Is there polarity to the flow of these ions through these channels if you reverse the polarity?
Yeah.
Yeah.
Well, I mean,
they'll
sure.
go in the... Right.
Unless it's a rectifier.
Right, unless it rectifies.
Yeah, unless it rectifies.
Right.
But the answer is yes. Your own experiments, you saw that.
Right, there was the... Yeah.
And I should mention, both in single channel patch and in macro patch on the salamander cells, just like in mammalian cells, if you remove the cytoplasmic side's magnesium, the rectification goes away.
Right.
Okay? And that's one reason that magnesium depletion...
Don't forget magnesium in the solution.
Yeah, don't forget magnesium unless you want to. But if people get magnesium depleted, they will waste potassium and become hypokalemic.
Mm-hmm.
So again, here's our principal cell with the two big players, the ENaC, which is making the sodium disappear as it gets reabsorbed, setting up the driving force because of more negative lumen for potassium to be secreted through ROM K. And then, there's probably on the intercalated cell a maxi K channel. So this is what's going on in terms of the kidney. So there's the normal physiology. I just wanted to show it right side up. The aldosterone binds to the mineralocorticoid receptor. The mineralocorticoid receptor has several actions, including increasing the overall open probability of activity of ENaC and stimulating the pump. And that's great. It makes sense. It would have an action on the apical membrane, action on the basal membrane, and then potassium follows right along. This is also important. Cortisol can bind to the mineralocorticoid receptor. It doesn't because there's an enzyme called 11-beta hydroxysteroid dehydrogenase type 2, all in the collecting duct. This enzyme quickly converts cortisol to cortisone. If it didn't, cortisol could bind to the mineralocorticoid receptor. This happens at Halloween. So at Halloween, what happens is people eat
licorice.
They eat black licorice. Now, black licorice, it's a genetic, you can have a genetic defect in this as well. But people that eat a lot of black licorice, and I've had patients, several. One was a neurosurgeon who came in with a stroke, and it ended his career because of his licorice. He was eating the high-test stuff from Canada.
Oh.
So when you eat black licorice, glycerotinic acid in the licorice will inhibit the enzyme. So now cortisol levels will abnormally build up. And what they'll do is they'll bind to the mineralocorticoid receptor. It's called SAME, the syndrome of apparent mineralocorticoid excess. Right. So licorice gives you SAME. You can be born with SAME, but licorice gives you SAME. The aldosterone levels are negligible because they're all suppressed by the volume overload.
Right.
Because the cortisol's driving it all. But that's why it's one of the forms with Little syndrome. It's one of the forms of pseudo hyper aldo. It looks like the aldo levels should be high, but they're not.
Mm-hmm.
But the cortisol levels are. So again, it's just the same thing. It's the same pathway. This is not supposed to be a player, and it is if the enzyme's blocked. Okay, so renal, getting into where hypokalemia may come from, let's look at renal potassium and chloride loss, because both renal K loss obviously would cause hypokalemia, but also chloride loss, like we said in vomiting,
right.
Chloride depletion. So you can divide these into the ones where the ECF volume is low or not low. So when it's low, you can have an upper GI loss of HCl, and that would be vomiting, whether it's vomiting, bulimia vomiting, or physician-assisted vomiting.
Right.
Now, when you have sodium chloride loss prior to the ASDN, that's what's going to happen with loop diuretics, and of course, Bartter syndrome is like being born on furosemide. And thiazide diuretics, that's like Edelman's like being born on thiazide. All of these are going to give you hypokalemia through the mechanisms we just showed. And then to add on to that, because we just mentioned intracellular magnesium is needed for K channels all over the body to inwardly rectify, magnesium depletion, if you get cytosolic magnesium depletion, K will leak out of the cells through the K channels instead of being inwardly rectified. It'll be more omic. That potassium will come out. It gets filtered at the kidney, and it's going to go out because aldosterone levels are going to go up. So one reason, I mean, we see hypomagnesemia and hypokalemia together a lot clinically. So any patient, the first thing you do in any patient with hypomag is you make sure they're not hypo-K.
Right.
And you also know when you're trying to correct hypo-K,
you make sure they're not hypomag.
I mean, so it's always on the boards. Oh, this hypokalemic patient is not responding to K. And the answer is because the patient's hypomagnesemic and we didn't check. Okay. So this is the slide of hypokalemia when it's being mediated by renal K and chloride loss. Even the magnesium depletion is being mediated in the end with that. Now, hypokalemia and metabolic alkalosis go together, just like hypokalemia and hypochloremia go together, just like hypochloremia and metabolic alkalosis go together.
Right.
So they're all tied together. And that's why I don't like, when everybody has a separate chapter on these topics, you lose the integrity.
Right.
How
it fits together.
We know that peanut butter is good.
Right.
We know that jelly is good.
Right.
But come on.
Right.
It's when you put the peanut butter and the jelly on the bread and you put it together. And that's when
the magic.
That's the magic.
And
so every one of these talks, we're trying to make like a peanut butter and jelly sandwich instead of just being peanut butter or jelly. So again, here's the gut losses again are diarrhea where you're losing potassium and bicarbonate. Laxatives, you could be losing this too. And then the renal ones. The renal ones, see, you're hypokalemic and with metabolic acidosis in diarrhea and laxatives, and then renal K loss with the effective proton secretion will give you an acidosis, and we already talked about the renal tubule acidosis, the type 1 carbonic anhydrase RTA in a bottle, the type 2 proximal, the type 1 distal, and of course we'll get into the other one, but they give you hyperkalemia.
Right.
Now here is renal K and chloride loss made worse with primary metabolic alkalosis, and that's the ones where the volume is too high. This would be your primary hyperaldo, like we mentioned, adrenal adenoma, Cushing syndrome, or a paraneoplastic syndrome of a tumor like a lung cancer. In your career, how many times have you seen a hyperaldosterone as a part of cancer paraneoplasia?
I have not seen it.
Okay. So before you, well, wait a minute. When Tobin was a fellow after you. Yeah. So one story you might enjoy is when I was precepting Tobin's first clinic. His first clinic as a fellow. And he comes in and he tells me that he's got a 63-year-old man who's on a zillion antihypertensives. He's spending a lot of money on these medicines. And his chief complaint is, and I said it at the same time with Tobin, I said, his chief complaint was not the money, but the sex. Okay?
Right.
He was on a boatload of antihypertensives, and you have seen every day
Right.
the complaint of, I mean, it's very important to talk to our patients
ED.
about sexual dysfunction related to
Exactly.
medicines.
Right.
So this guy's spending a boatload of money, and his blood pressure is not good, and neither is his sex life.
Right.
So the guy, of course, when you have money problems and blood pressure problems, and your sex life isn't good, you got to come to see us.
That's it.
We're the ones.
That's nephrology right there.
Exactly. We're going to take care of the whole patient,
That's
including
it.
financially.
It's always the big picture.
Right. So the big picture was, so then I'm thinking to myself, okay, hypertension, and it's pretty resistant to drugs. And then Tobin gets to the electrolytes, and the electrolytes are screaming. So his sodium concentration, of course, is fine, but his potassium is low. It's in the low 3s. His bicarbonate is high. He's got a hypokalemic metabolic alkalosis. And so let's see. So you've got high blood pressure, hypokalemia, and metabolic alkalosis. And so I say to Tobin, you're a lucky man.
Right.
On your first ever nephrology clinic evaluation, you've got something fairly rare.
Right.
And he said, it can't be. You only see that on a test. And I said, what is it? And you're seeing it in real life. And he goes, are you saying he's got an adrenal adenoma? I say, well, he's hyperaldo, and the most likely thing is, and then we did the follow-up, and the imaging showed that. So we put the guy, we stopped everything.
Right.
And we put him on
spironolactone.
Exactly, or eplerenone, one of those two. And his hypertension dissolved.
Perfect.
His hyperkalemia got better, and so does metabolic alkalosis. Now, ultimately, but he could go a long time on the eplerenone, but they just watched the adrenal adenoma for a while because we were controlling it medically. Ultimately, he got it out. But the whole point was, this happened on his first clinic visit with Tobin, and it's great.
Awesome.
So there's the adrenal adenoma, Cushing syndrome, and the paraneoplasia. Of course, we were worried about that. We were happy to see the benign adenoma because it wasn't this. And then there's pseudohyperaldo, and we mentioned the licorice. You can be born with it, or the black licorice, the syndrome, the same. And then little syndrome, of course, is when ENaC is just, as we mentioned before, ENaC is just hyperactive from a genetic defect. It's staying in the membrane, not being pulled out of the membrane.
Being trafficked out.
Right. And so essentially, it's like your aldo's high all the time without being high. Since the sodium, ENaC is the rate limit set for sodium reabsorption in the collecting duct.
It shows you what's in control of that. The fact that if you can adjust the conductance, that the sodium goes up without affecting the pump, you know the driving force is, you know.
So the hyperreabsorption through the channel raises ECF volume and blood pressure to the point that aldo is suppressed. So even though they look all the world, they got the classic triad. All these people have the classic triad of hypervolemia, hypertension, along with their hypokalemic metabolic alkalosis. But these people, as opposed to the people with the adrenal adenoma and the paraneoplasia where the aldo levels will be high, these people, the aldo level's low, and that's why it's called pseudo-hyperaldo. Okay, so, and I've been lucky enough to take up, I think in Vermont, every family that had Edelman or Little were seeing me in the clinic. And that's very lucky to have those. It's very rare disease.
Yeah.
But not so rare in the family. Little syndrome is autosomal dominant. I just want to remind people, 1962 article by Grant W. Little, who discovered this. That's why it's called Little syndrome. In a 16-year-old girl or woman who was very hypertensive at school. She was one of 11 children. And when they went and looked at the family, all of whom had died of strokes.
Right.
Okay. 7 of the 11 kids were hypertensive with hypokalemic metabolic. So this was really dominant. 7 of 11 is even more than the 50% you would predict. So it's rare, but within the family, very common. You know, it's like a lot of the Michigas.
Right.
Okay. So now, so this may be so other causes that you have to look at in addition to primary hyperaldo is renal artery stenosis, glucoid remedial aldosteronism. Have you ever seen a case of that?
Never.
I was lucky enough to see a case of that because Rick Lifton wrote a Nature paper about that before he came to Yale. And then he had a lab where these patients would come to Yale, and I was able to see these folks. These are people who they're because of a mix-up in sort of the DNA. What happens is that the control of glucocorticoids and aldosterone gets confused, and aldo levels are high and actually responds if you give them glucocorticoids. And then there's drugs like fludrocortisone, the black licorice we talked about. And there are some people, rare people, again, I only saw one case at Yale, gain of function mutation in the mineralocorticoid receptor. But you can have, I mean, anything you can see, there's always a mutation.
Right, and that's why if you understand how the cell works and what the regulation is, you can figure these things out.
Yeah, so you have said, of course, the key sentence I love to hear it more than I like to say it, which is everybody, there's a long time the reputation of nephrology being difficult, intellectually or whatever, because a lot of it is we make it harder than it has to be.
I carry the model of the principal cell in my brain, and it's been so helpful. It's one of the tools I use the most.
Right at the bedside.
Because it's so frequent that we come up with things where you need to think about that.
Exactly. So my message is, for people that are intimidated by nephrology because of the reputation, there's two things about the reputation. It's got the reputation of being difficult, and the people who have given it that reputation are responsible for having it because I don't think nephrology is difficult. I think if you take the time to really look at the physiological underpinnings, it falls right out.
Yeah.
And that's why we're doing this. Because
and these diagnostics are fun. I mean, you think about them and you try to, it's like neurology. I mean, I had a great friend in med school who loved finding the lesion. All right, get an MRI. But, you know, when you can examine the person and find, and, you know, identify lesion, this is like that. We're identifying the lesion. Where's the problem? But we're using metabolics and measurements to sort it out.
Exactly. When I did my residency, we already had fancy stethoscopes, but we also had fancy echocardiograms. And so residents were saying, well, wait a minute, I don't need my stethoscope to diagnose a heart murmur. I get an echo. And we were lucky enough to have residents in our program that came from South Africa, from Witwatersrand.
Right.
And these people,
they were better than an echo.
They were better than an echo.
Right.
I mean, it was amazing what they could hear and feel and see. So you really, and again, there was nothing like that.
Yeah.
And I think it's getting to be a lost art with our technology, but you can't forget your roots. I think there was a movie about that. Okay, so again, here's just the whole summary slide again, and I don't need to belabor that. So one thing I did want to measure is, again, one of the figures from the chapter I wrote, there were no good figures in the literature that capitulated all this stuff. And so in addition to ENaC being activated by Aldo, I also wanted to point out little appreciated things that are great papers in the literature, that there are some older studies that show that increased ECFK also increases membrane surface area. So again, if you're trying to secrete potassium, an increase in ECFK, if that puts more foldings in the basolateral membrane and you get more pumps, that's going to help you. So in addition to the classic ENaC pathway with Aldo, there's this effect of ECFK that will stimulate the pump directly and also may lead to remodeling of the basolateral membrane. And there's a flow effect on ENaC. So it's been a little controversial it was 20 years ago that in our lab, we were expressing ENaC in oocytes, and we saw flow activation and wrote a little thing on it and came back rejected because they said everybody knows that ENaC is not mechanosensitive. And then about a year later, there were some papers from other groups, and all of a sudden ENaC was flow regulated. It's still a little controversial, but there was a recent article in Nature, or at least in Nature Reviews Nephrology, that shows all the ways in PKD and other things, the cilia. This is the principal cells where the primary cilium is. If something's going to be regulated by flow, and we already know that flow regulation through the primary cilium is regulating a lot of stuff down there that's relevant to PKD and regular physiology, and certainly the MAXI-K channel is regulated by flow. It could also be that ENaC is regulated by flow, and why not? Because by doing that, flow would become caluretic. And we learned, one of the first things I learned on my first day of fellowship, Peggy Bia came in, and she's a little bit of a character. She's great, and she's from Brooklyn, with the thick New York accent. And we had a case of hyperkalemia. And she would say to me, Alan, you can never forget. You never forget oliguria is going to cause hyperkalemia.
Right.
Because you need urine flow. So that's why we always like non-oliguric AKI more than...
Maybe this is trying to keep that ratio from that New England Journal article balanced.
You know, it's great that you say that, because what you're doing, see, by looking at the cell diagram and this is what I love about you. One of the many things. But
There are so many things I love about you.
But what I love about you is you'll look at this cell diagram, which you already have a love for because of the physiology and the pathway.
Yeah, I mean, I know
but
the
then
basics.
you'll immediately link to the thing you just saw for the first time today.
Right.
You just saw this New England Journal paper, and your mind is thinking about it in the background, and all of a sudden you want to make some connections.
Yeah.
And this is what makes...
That's the beauty of these things, is trying to put the mystery together.
Exactly.
And the magic of it. And look, all the reasons we see these mortality benefits and these things that they show in slides.
Yeah.
There's a reason behind them.
There is.
What is it? And it's got to do with the membrane most of the time.
Right.
And that's channels and pumps. And
if deep learning can tell us more about those membranes?
And that's the other, I think we're getting
That's where
there.
that's your side of it. And I think it's great. You know, I love to use the word...
That is super interesting.
I love to use the word demystifying because I have a talk actually for the med students called Demystifying Dialysis. Maybe we can do that as a podcast.
Hey, that would be good.
It would be because you know a little something about that. Have you ever? Let me ask you this, Craig.
I do a lot of dialysis.
You've never seen a patient with glucocorticoid-remedial aldosterone. Have you ever seen a dialysis patient?
That I've seen.
Yeah, you've seen. So it's fantastic. But you know,
trying to see less.
One of the things I think is a shame about this chapter. I mean, I really worked hard on this chapter, and it's in a book that nobody's going to buy.
I'm going to buy it.
No, you have the chapter. You have the chapter. I send you the chapter.
I do have the chapter.
But the whole point is, though, you can...
Except I want to buy the book, and I want you to sign the book for me.
And here's the another figure. There's only a few figures in the chapter, and here's the other figure that shows the intercalated cell, the alpha intercalated cell. Now you don't see ENaC, but you see the maxi K channel that's stimulated by flow. And then in addition to the sodium potassium ATPase on the basolateral membrane, the alpha intercalated cell also has this very interesting, and here again, there's got to be a link. There's got to be a link between. So people say, well, I don't understand why hypokalemia and metabolic alkalosis or hyperkalemia and metabolic acidosis are linked. Well, have a look at this.
Maybe there's the link.
I'm not sure, but this could be the link. So what does this tell you? This tells you if you're hyper secreting protons, okay, you're going to get you're going to get reabsorption of K. So there's going to be a relation between acid. So if for anybody who says I don't understand why K homeostasis and acid base homeostasis are related, there you go.
Right.
So just like this pump, and the New England Journal article is on sodium and potassium excretion. These things have been linked for a long time. Okay.
It is interesting.
So
they should have. I got to read the article. I actually haven't read it, and I'm going to read it now.
Well,
the
figures are
super interesting.
The figures are super interesting. The article, I have to say, the text of the article, I think they really did a very careful study. The text of the article is less about the findings. I shouldn't say that. It's equally about the methods to really show you that they did it right. So it's very reliable. So again, we mentioned this with RTA, the urine net charge. I just want to give you a couple of examples. So if I've seen patient with diarrhea. When you have diarrhea, your volume depleted. So your kidney's going to not waste sodium. So the urine sodium's low, and the kidney's not going to waste potassium when the gut's wasting it. So what you get is a low urine sodium and urine potassium, and because you're losing bicarbonate, I mean, this is volume.
Right.
This is hypokalemia, and this is I'm losing bicarbonate, so I'm going to have a big urine chloride. And the urine net charge is, of course, a big negative. And then, of course, here, as we talked about with the RTAs, where you have K loss and defective proton secretion, the urine net charge, again, there's no reason for the urine sodium to be low. The urine potassium will be what it'll be, and the urine chloride's not revved up, so you get a positive urine net charge or anion gap, and that just reviews what we talked about last time. So we've talked a lot about hypokalemia. I don't know who did the animation for this slide because it's coming up randomly.
I never would have done it.
But it doesn't matter. Let's just see what happens. So major causes of that's good. Major causes of hyperkalemia.
That was the perfect order.
That's the reverse order. It's keep you awake. It's fantastic.
I love it.
So hyperkalemia, major causes. Well, we mentioned it before, cell lysis. When there's all this K inside the cells, it's a disaster. I mean, these membranes have gone to all this trouble to keep the K in the cells. The pump and the membrane is devoted.
Right.
And all of a sudden, you blast the cells open.
And if there's a big tumor burden or there's a big crush, you got a lot of potassium getting released.
Now, how often are you seeing lysis syndromes in your practice?
I see a lot of... I see a lot of marginal tumor lysis syndrome
Yeah.
not leading to dialysis, for instance,
Good.
but I see people with hyperkalemia, hyperuricemia, all the typicals, hyperphosphatemia after chemo,
Yeah.
you know?
So I again, like you, I've seen tumor lysis cases.
Yeah.
I thought I'd like to make a couple comments about rhabdo, because rhabdo and me, we've been together a long time, and here's why. At Michael Reese Hospital, the last few weeks of every year grand rounds, the weekly grand rounds, was the top 4 or 5 graduating residents would get an unknown case. And they had to do it New England Journal style.
Oh, that's
where
great.
they have to go through the case, make a presentation, and then basically say what was the diagnostic test and what was the diagnosis. So since I was pre-renal,
Right.
they gave me a chart of a woman, not an older woman, but a younger woman, who had AKI and electrolyte abnormalities. And the hard part wasn't figuring out it was rhabdo. The hard part was putting it together a talk on rhabdo. Because I mean, the diagnosis was clear, and again, I said, well, and what's the diagnostic test going to be? I mean, you don't need a kidney biopsy, but that's what it was. They did a kidney biopsy, but that's what it was. But anyway, ever since then, I've been close to rhabdo. The very first case I saw as a Yale fellow, I had been handed a half a donut and a beeper, and
And it went off.
the donut exploded, and the beeper went off. So the beeper goes off. And it was the SICU calling, right. and I had to ask somebody, how do I even get there?
Right.
The first patient I saw was a man. It was 95 degrees or 100 degrees in New Haven that day. It was July 1st, and it was very hot. And a muscular guy, African American guy, had flipped his Jeep over and was pinned under the Jeep on I-95. This guy comes into the SICU with multiple trauma, and he had an initial CK that was immeasurably large. We just knew it was more than 500,000. Okay? They couldn't measure it beyond that. I ran up to see him and got the last 3 drops of urine he was going to make.
Right.
The urine showed the classic findings of dipstick positive for blood, but no red cells,
Right.
and a zillion muddy brown casts, and it was an orange-red urine. Okay, so he died. The bottom line for that guy was they told him his kidneys were shot.
They regenerated.
And
You gotta love tubules.
I told them, I tried to say, because a month went by, no urine. 2 months went by, no urine. 3 months went by, no urine. Everybody's losing
and
hope.
you can see the tubular cells just lining up and getting ready for the switch to go on.
And I got money on this.
Oh, yeah.
I put $1 on it.
Yeah.
And so everybody was saying, no, these kidneys will never come back. 4 months, he opens up.
And it's fast when they open up.
He opened up and got off dialysis in 3 days.
Amazing.
So it was fantastic. So that was my next brush with rhabdo. And then when I was a research fellow at Yale, a young muscular kid went jet skiing on the Long Island Sound with the bumpity and sat in a way that the waves bumped up against his gluteals.
Wow.
And he came in with jet ski rhabdo.
That's a good one.
And then the last story of rhabdo I want to tell you is not long after I came to Vermont, I got called in on a Saturday night to see a young kid, 26, with orange-red urine. And the reason why I talked to the kid, I said, so what was going on? He goes, well, we were skiing and we're drinking beer. And I go, well, you got rhabdo. And so it turned out it wasn't his first time. So what he had was a defect in the carnitine shuttle pathway of his muscles. So he had a genetic defect predisposing to rhabdo.
Right.
And the thing that would make him have rhabdo is mild trauma, mild to moderate trauma combined with alcohol.
Right.
And what he loved to do was go ski the moguls and drink beer.
Oh, geez.
So I not only saw him once, I saw him again. And I said to him, you might want to think about, going down the smoother pathways and having a little less beer. He goes,
Right.
he goes, okay, but I'm going to tell you, I like beer.
On this side of the lake, my one good rhabdo story was a young guy, super fit, very muscular, and of course he's incarcerated, recently incarcerated, and they decide they're going to have a squatting competition.
Oh, yeah, that'll do it.
And so they just did squat, squat, squat. I think he did like 1,500 squats.
Yeah.
And he had sore legs the next day, so they pounded him full of ibuprofen.
Exactly.
And I was like, perfect.
Exactly.
Well,
and that's right. The combination of the exertion and then the inflammation with the nonsteroidals treatment is going to give it to you. And I've seen somebody, I think he was from this side of the lake, and had come over.
I think I remember a case with both of us when we had a super marathoner in Burlington.
Yes.
100-mile race.
Yeah, ultra marathoner.
Yeah.
And there was another case we may have been involved with. A guy came over from Plattsburgh. What happened to him is he decided to eat fentanyl, which I didn't think was very good, especially without cheese. So he eats fentanyl, and then he falls asleep for 1,000,000 hours with his leg pinned under him. So his whole leg dies, and he gets a compartment D syndrome and a rhabdo. And so this is what happens. And so we had gone from, back to my original case in Chicago. The woman was a drug abuser and had rhabdo. Then there was the trauma of the jet ski guy and my guy with the beer. But it's the non-traumatic and traumatic, and the fentanyl guy, it's trauma, but related to medical conditions.
Yep.
So anyway, these are the things. Now, the one thing we don't see too often, except on boards and in books, is hyperkalemic pyrrhatic paralysis. That's talked about in the chapter. Anybody who really wants to know more about this, believe me, I'm happy to send you a signed copy of this chapter because this
there'll be a link in the subscript.
Well, you can't get it through a link. It's only this PDF I sent you. I photograph it.
Oh, that's
so
awesome.
So actually, if you want it, we'll be happy. Just let us know. We'll be happy to send it. I'd be delighted to send it to anybody. Good luck. But if you do want to know,
can you order the book?
You can order the book.
Let's plug the book. Where's the book?
I'll get you the book.
All right.
I'll get you the plug. We'll put it in the.
All right.
We'll put it in what they say. Look.
Yeah,
below.
just click here.
Yeah, click here. So, but the thing about it is that the chapter, I like it. And I've read a lot of potassium reviews and chapters, and I wanted to write one that I would understand. And I was telling you before we started today, as somebody who wrote a chapter on potassium, I read my chapter, review it. And I go, when you write something, you remember. But I go, it all makes sense to me. Yeah. And then the funny thing is, I'll go read some other potassium review and chapter, and I'll be sitting going, oh my goodness, I don't understand it.
That's because the person writing it didn't really understand it. And one of the beauties is your deep knowledge of how these channels work and the interplay of these regulatory processes helps people get it. And it's fun.
I hope so.
And so it stuck with me for 20 years. I'm a clinical country nephrologist, and I still draw pictures of the cortical collecting duct.
Yeah. So this is so for anybody who has got more questions, I guarantee you ad nauseum in the chapter. The old saying my friends used to have for me in college: if you could say it in 10 words, Alan will say it in 10 volumes.
Right.
But I've tried to get better at being long-winded. So then there's these things where anything that interferes with K secretion along the nephron, we now know for sure you would predict this would be the case. So if you can't fool with the mineralocorticoid receptor, you can't, the mineralocorticoid can't be deficient, and the receptor has to respond. So we all know hyporenal hypoaldo seen in diabetics, distal type 4 RTA comes in here, and again, no shortage of medications. Let's just see. This is a table. These are a couple tables out of the book, out of the chapter. And, I'm not going to read it to you, but you can see there's huge numbers of causes of mineralocorticoid deficiency. And then there's hyporenal, hyporenemic, hyperaldo. And then mineralocorticoid resistance because of a huge long list of drugs. But look at the drugs. They're either blocking aldo or they're blocking ENaC. And there's more and more drugs that block ENaC. These are just the first 4 I could think of. But these still are they're important to keep these in mind. And then any kind of kidney disease is going to do that. So, again, you're not surprised to see these people with kidney issues and interfering with the renin. The kidney can be fine, but if you interfered with the RAS system, you got to play with that carefully. Here's more clinical conditions that predispose, and the big ones like diabetes and type 4 RTA. Other drugs, sometimes ones you don't necessarily think of, like calcineurin inhibitors. You can't stop calcineurin inhibitors on our transplant patients, but we have to be aware of the fact that they interfere with K disposal.
Regulation.
And then look at the list of antihypertensives. And this is incomplete because it doesn't include the ones, there's only ones up to, phenerone, would be on C here now.
Right.
So you can tell though, the chapter.
It's growing.
The good news about the chapter is even though it's 2013, it's still pretty up to date. The bad news is it's not fully up to date.
Right.
It doesn't have that New England Journal paper in it, and it doesn't have phenanerone in it. But look at this. What are they all? They're all ACEs or ARBs or angiotensin antagonists or ENaC blockers or beta-adrenergic blockers.
Right.
You know, you got somebody on beta blocker. You got a diabetic.
It's usually multifactorial.
Yeah, it's multifactorial.
These are the things.
But you're diabetic,
Right.
who's hyporenin, on an ACE inhibitor, an ARB, and a beta blocker.
And getting heparin injections.
Yeah, getting heparin injections, and heparin's got to be on
It
here.
is on the list.
Heparin's got to be on
drugs,
here,
right.
on there somewhere.
Under cyclo, under COX-2 inhibitors.
Oh.
There you go. Heparin and...
Yeah, I can't really see, but
There
if
you
you
go.
say...
Number 4.
Oh, heparin and congeners.
Yep.
Oh, right. See, and how does... By the way, here's a board's question for you. How does heparin... We didn't practice this. How does heparin... Why does heparin predispose to hyperkalemia? What's the mechanism? Is it ENaC? What does it do?
It inhibits aldo's effect on the sodium potassium ATPase.
That's an excellent guess.
But it's
it
wrong.
Could be better.
It could be better.
But
it's not on. It's not an effect on ENaC.
Like I used to say to
I'm
you.
gonna say
like I used to say back in the day. It's a good guess, but not a great.
Let
guess.
me guess. Let's do apical membrane versus basolateral membrane.
You're getting colder.
All right. So it's okay.
You're getting colder. Yeah. So it's interesting. People have it on their list now.
Is it the mineralocorticoid receptor?
No. Okay.
All right.
So good.
Go ahead.
You can see we didn't practice it. But you see, the thing about it is you've known for a long time clinically that heparin does it.
Yes.
And you'll look for that right away in a
always,
patient.
when I see
Right.
a hyperkalemic patient, I look for my list of things
Right.
because it's usually multiple.
And, as a country doctor, you don't need to keep at the foremost of your mind what the mechanism is. But across the lake...
But that's why I love these discussions.
Right. So here's the answer.
Because next week I'm going to remember this.
Here's the answer.
Go ahead.
Heparin and some of its congeners interfere with an enzyme called aldosynthase. So the effect is going on in the adrenal zona glomerulosa. So heparin goes into the zona glomerulosa and interferes with the enzyme. And
reduces.
I don't know much about biochemistry, but even I know that aldosynthase probably has something to do with aldosterone
production.
Synthesis. Exactly. And that's what it does.
But I did say it was its effect on the sodium potassium ATPase through inhibiting aldo.
Yes.
But the problem was it was in another place in the body.
Right.
I gotcha.
So again, for people that want those details, and again,
listen to the podcast.
These are the Easter eggs in the chapter.
Oh, God, this is gorgeous.
If you call that Easter.
This is so fun.
Okay, now here's something that I put in the chapter that is introduced for the first time, and I've gotten a lot of good feedback on this, and it's been bugging me since I was a resident. So you now know, with 98% of the K inside of cells, and only 2% outside, what I was taught as a student and a resident is that the way you replete potassium in somebody is there's some linear relation that's going to tell you, and this is the biggest dog being wagged by the tiniest tail.
Right, yeah.
And you're going to tell me this tiny tail. So what I did, I said, look, there's no predicting this. Certainly not linear. So I had a hypothesis. I went into the literature.
I was going to say, one of the things I was going to talk about was Alan's going to present his correction for potassium in the setting of hyperglycemia.
No, it's not quite that, but it's along the same knot lines.
All right.
It's along the same knot lines. And what I did was this. I went back in the literature as far as I could. The best study was the 1981 study by Rick Stearns. And I found all the times that people had made careful measurements of not only the serum potassium in a patient, but their story and the drugs that they were on, and how much potassium it took to fix them. Okay? And then I used a little program that you know.
Excel. Your
Origin.
favorite? Origin.
And what I did was I made two plots. I said, if the ECFK is on the x-axis, what function would describe how much total body potassium they could be depleted? And here was the answer. So the first black line here is just the line that I was taught as a student, this crazy linear thing. And you see the linear thing works fine when the potassium's pretty normal.
Right. Until you need potassium.
And then
it falls apart.
Yeah, so it's great. It's great until you need it.
Until the problem arises.
Right. So I took from all the studies that I documented right on the slide.
So funny.
Okay. I took all the studies on the slides, and I plotted every data point. Okay. A little, the blue ones with the dots from Stearns and then some others. And I had a patient of my own, I think I put on this. And then I said to Origin, here's your data. Let's just go with an exponential fit. So the first thing I fitted to was a double exponential because I said, why not? But I found out that the double exponential second component was so tiny that it only needed one component. Now, what did I like about this exponential that Origin generated? Two things I liked right away. First of all, you got to like the boundary conditions. Number one, what it told you was when the K was normal. So this equation here, this is the equation. When the K is normal, and this is easy to put in Excel. When the K is normal, the thing tells you that you don't need any.
Right.
There's no deficit. When the K is really low, like so low that's not compatible with life, like nobody's seen too many Ks below 1. Okay, but I said, what happens if the K is like
it tells
0.1?
You need the total body potassium.
It tells you need the total body potassium.
Isn't that awesome?
Yeah,
it works.
It works.
It works at 0, which is the best.
And then some dialysis folks, what they like about this, most clinicians and us are interested in helping it predict the deficit. But what I've seen a lot of my colleagues who dialyze people and deal with people with very low GFRs, what they like was they like to use the other side of the equation. The number of potassium millimoles needed to be removed to bring a K from 9 to 8. You know what the number is? 9.
Right.
9. It's tiny. And the equation does it. So let me just show you a little bit about this equation. And I lost the...
sorry.
I got it.
Oh, good. You're back?
Yeah.
Okay.
So here's something from the literature. This is a 43-year-old woman with weakness, a lot like my 21-year-old. Weakness, potassium 1.2, and that's pretty low.
That is low.
That's low.
That's scary low in a 43-year-old
But
woman.
look, to have a potassium and 2 and a bicarbonate of 15,
right?
This is amazing because this is not hypokalemic alkalosis. This is hypokalemic metabolic
acidosis.
And look at the urine pH.
Wow.
The urine pH is 6.73. So this woman, who I think had Sjogren's syndrome, they documented that they needed to give her 1,050 millimoles of K. The equation predicts 1,100.
Perfect.
So I was pretty happy about that. This is a paper from what,
2008.
Yeah, 2008. Okay, so let's go back to my 21-year-old. No genetic disorders. Glucose is fine. Blood pressure is fine. She's got acidemia, or acidosis, sorry. And then her urine net charge was very positive. So we knew it's not the diarrhea laxatives. People said, "Oh, we think she's got an eating disorder, and she's abusing laxatives." No, wrong urine gap. So it turned out that she had a type 1 RTA, and this RTA, her urine pH. It's on here somewhere.
Yeah, it was above 5.5.
Yeah, I think it was 6.3 or something like that, 6.5. Anyway, she had, and she also had kidney stones. So this is I followed her from my whole fellowship, from the time she was 21 to 82, because my fellowship. and so, this was just her. And so the poor thing got so hypokalemic she couldn't move and formed kidney stones, all part of a distal RTA. Now, the equation, which I hadn't developed yet, would have predicted she would have needed 626 millimoles of K. So anyway, let's talk about treatment for a second because we're finishing up. So the principles of treatment of hyperkalemia are not that difficult. First of all, you always prefer the oral route because let's face it, that's how we've been doing it.
That's it.
Okay. So if you have to use potassium intravenously, the rule is low and slow. It burns. Got to be you got to be through a central vein if you got to give a lot.
If you can.
So hypokalemic metabolic alkalosis, give KCl. I mean, you're not going to fix the alkalosis as long as the hypokalemia is there. So you can give, like, if there's acidosis, like this lady with the stones, I put her on K citrate. She needs the K and the citrate, or K bicarbonate, because she needs to have potassium and something that's going to turn into bicarb or B bicarb.
Right.
So polycitra is one of the things that I had her on because she had the hypokalemia metabolic acidosis. Now, again, if you must use IV, then go low and slow, never exceed 20 millimoles of K per hour. That has to be a central vein because it's going to be caustic. Acute treatments. Here's my little one-slide multi-pronged treatment of how you approach hyperkalemia.
Okay.
First thing you do is exclude pseudo-hyperkalemia, which is usually due to fist pumping. So you want a tourniquet. But when you put a tourniquet on somebody, you just use the tourniquet. You don't need the tourniquet and the fisting. But on television, you see on television, don't do that, okay? So the things that will cause pseudo-hyperkalemia means that the specimen's hyperkalemic, but the patient
but the patient's fine.
Right. So it's fist clenching is the common one. Now, a couple interesting things. Now, the other thing is when there's a lot of white cells or platelets in the tube, those white cells and platelets can release their potassium. The tube becomes hyperkalemic, and it can help to do a serum versus plasma potassium. The lab can do that for you. And that if there's more of a difference in half a millimole, then you might be dealing with pseudo. Now, my favorite case of pseudo-hyperkalemia is this. It's not a case I saw, but it's a case I read about when I was writing the chapter. A father and daughter. I always tell my fellows, have I told you about the father and daughter? A father and daughter get into a minor motor vehicle accident. They're brought to the ER. They're fine. For some reason, blood tests were done. Both of them are hyperkalemic. Now, these are perfectly healthy people who are just in a minor MVA.
Minor accident.
They have no symptoms whatsoever, have no kidney disease whatsoever, and eat normal diets. So they get treated for hyperkalemia, okay? And then they have symptoms.
Right, exactly.
Okay? Here's what the answer was in that case. What they had was something very interesting. The father and daughter are related to each other. I can't remember how, but they're related to each other. And what happens is they have a mutation that as long as their cells, red cells, are kept at 37 degrees centigrade, everything's fine.
Right.
But when the cells get cool, the membrane leaks. And so they have a temperature-sensitive mutation. And all of their blood, once it drops below body temperature, is essentially lysed. It's not lysed. The cells don't lyse. The K just leaks out.
Wow.
So it's K leak,
Incredible.
not lysis. Yeah, I loved that case. I think they made me take it out because I was running long for a change. But anyway, that's a great case of pseudo-hyper but pseudo-hyper means it's simple. Pseudo-hyper means the test tube is hyperkalemic, not the patient. Now, the first thing to do, as I showed you, is protect the heart. And we prefer calcium gluconate to calcium chloride because it's less caustic. Now, when I was my first year in Vermont, I'll tell you a story that you were an intern. My first weekend on call was a Saturday. And remember, the Brown building had the dialysis unit, and there was a ramp up to the dialysis unit. Okay, so on a Saturday morning, and I see a guy come in, and he's walking up the ramp, and I see him stumbling up the ramp. Now, when you're hyperkalemic, it's an ascending paralysis. The big muscles of the legs go first. So he's having hip flexor muscle problem. And so I said, let's put him on a monitor. So we put him on a monitor. He's got wide complex. Okay, but it turns out that he had a catheter, dialysis catheter. So I asked for calcium gluconate, and the monitor is running, and I'm so mad that I think
you've showed me one of these.
I misplaced it. But anyway, the miracle was, here's this wide complex. I start pushing the calcium gluconate through his dialysis catheter, and as I'm pushing it, I see the QRS normalized in 3 seconds, correct?
Amazing.
And so the question is, how does that work? I'm going to give you
membrane stabilization.
Yes. So everybody says membrane stabilization, but now I'm going to give you a chance to. No, I don't expect. I would expect anybody to be able to answer this question. So I just think about it because I have no other life. Yeah. But given the fact that there's no doubt about it, if there was ever a doubt in my mind, pushing this and seeing it with my own eyes in 3 seconds completely fixed it.
Right.
Why? Without changing the potassium, of course.
No, but it changes the resting membrane potential.
How and why?
Because it makes it more positive on the outside.
Good. So what you're just articulated there is called the surface charge hypothesis. It was the going hypothesis for many years.
But this is where you go.
It's a good,
great
it's
thought.
a good hypothesis. No, it's a good hypothesis.
It's where they started.
But it's not a great one.
Okay.
Because it's wrong.
Okay.
And the reason it's wrong is because magnesium cannot duplicate it.
So I thought magnesium can.
No.
I thought,
no.
okay.
No. Nothing takes the place of calcium itself. The surface hypothesis theory was pretty much disproven because a divalent positive 2, divalent cation magnesium is, doesn't do what it's very calcium-ish. Got to be calcium. So now it's not surface charge like you want it to be. Okay. That would be the right direction. Wrong.
Right.
Okay. So now I'll give you one more shot.
Okay. It's not surface charge, but it affects some voltage-gated potassium channels.
Good answer. Good answer. Not a great one.
Okay.
I
was getting closer.
You were warmer. You got colder when you said sodium channel.
Don't torture us. Give us the answer.
So here's the answer.
All right.
And I'm not sure it's the answer.
Okay.
But it goes back to something that Clay.
Because this is something we all talk about.
Yeah.
Did you give him calcium glue?
Yes.
Right now, we're about to hear. Hold on to your hats because we're going to hear how this works.
So the thing you're going to read in every book,
all right,
and even in my chapter, it says protect the heart, stabilize the membrane.
Exactly.
What I'm going to tell you now.
That's the country nephrologist answer.
What I'm going to tell you now is how it's a hypothesis of how I think it does it.
Okay.
Or how maybe more than me. Anyway, here's what happens. Hyperkalemia depolarizes the cardiomyocytes just like it depolarizes everything. And that's going to destabilize the rhythm. So Clay Armstrong, a great biophysicist, did some work with squid axon in I think this was the 70s or maybe the 80s. Anyway, what he did, so squid axon is very useful. Hodgkin and Huxley used it because it's big, and you can change the exoplasm.
Oh yeah,
and you can do experiments. Another thing that you can do with squid axon that you can't do with mammalian is you can put it in a zero calcium condition. And with mammalian tissue, you put zero calcium on something. That's how we dissociated ourselves. Everything falls apart. The squid axon doesn't. What Clay Armstrong noticed, and I think it was a PNAS paper, what he noticed, and it might have been 1990 when the paper came out, when he removed calcium from the exoplasm of the squid axon, he noticed that voltage-gated sodium channels could not close. Here's the hypothesis. Voltage-gated sodium channels open right away, and then they're supposed to close right away. But it turns out that voltage-gated sodium channels won't close in a vacuum. They want to close around a calcium ion.
Ooh.
So calcium is required for voltage-gated sodium channels to close. And when what happens in the action potential is the voltage-gated channels open, and then the old sort of ball and chain, the ball comes up and blocks the pore. Okay, and that's how they inactivate. To have that happen requires calcium. Right. So I believe, and there's no proof of this, there's proof that the surface hypothesis is wrong.
Okay.
And then there's a lot of people that do a lot of
discussion
sword
of
guide.
What are the right, exactly.
A lot of sword guide. But the Clay Armstrong to me is the closest to the Indiana.
Interesting.
And what that is giving back the calcium protects the membrane, because what it does is it makes the heart myocyte not feel as depolarized as it did, because now calcium is available for those voltage-gated sodium channels to close around. And if they don't close, they can't, inactivation has to be removed by hyperpolarization. Right. Everything is going to be screwed up. That's why this is fatal. Okay. So one thing I did want to do, and I'm very happy that you gave me the drum roll, because this is something I want to give people that people don't have all the time. So this is hypothesis, but I think it's the best one I know. Now, the other thing that we should be stressed is you got to correct any hypovolemia. When somebody's down a liter or two of saline, giving them a liter or two of saline with no potassium in it goes a long way to decreasing the ECFK. Of course, the way we do it clinically is we shift and we try to do what the zebra would do, insulin and beta agonists. You try to stop any of the medicines. And again, a study was done asking how many, they took a bunch of nephrology consults. This was done in Vermont. They counted a number of hyperkalemia consults and said, what number of patients that we were called to see for hyperkalemia were actually taking K? Guess what the number was?
Unknown.
33%. So 1 out of 3 hyperkalemia consults, you write suggestion
Stop
giving.
the potassium. It's huge.
It's huge.
It's huge.
It's huge.
We see it a ton of times.
It's huge. And then in the end, so these are the things
and literally, I'll get the consult, and the doc will be saying, I always say, are they on a potassium supplement? No. And then I check back, and
they are.
They've been on it.
Yeah, they've been on it so long, nobody knows.
Yeah.
So when you're treating them acutely, calcium gluconate works fast, but you have to be ready to give it again. It's not going to last very long, maybe 15 minutes, 15, 20 minutes. You temporize with insulin and beta agonists while you call nephrology.
Right, exactly.
And then you get rid of these medicines, but again, getting rid of a medicine is not going to fix the problem right there. And then what do you do to remove the K from the body? Well, if the kidney's in the game, if you can get the kidney back in the game with volume, get the kidney back in the game. If you can't get the kidney back in the game, try to bind K with the newer agents, Lokelma and Patiramor. Okay. Also, try to get the kidney back in the game with caluretics. I've used acetazolamide. I've used fludrocortisone. I've used lupin thiazide diuretics to promote K excretion, even with AKI. I remember in the SICU one time a guy needed surgery, and hyperkalemia was making him not do the surgery, and we gave him fludro, and that got him to go to the surgery. And then, so this is what you do, and then nephrology comes for the hemodialysis. There's only two comments I want to make about hemodialysis. Okay. One is the serum potassium is important, but what is underappreciated is you don't fool with the rate of changing potassium. So not only is the steady state,
the bulb always blows when you flip the switch.
Exactly. So this the parameter of the ECFK is important, but the first derivative, delta K over delta T. In fact, it's believed most dialysis deaths happen after the long weekend. They happen either on Monday or Tuesday.
Right.
I mean, that's well shown.
Right.
Even the country nephrologist has seen that.
No, for sure.
So, and the reason it's now hypothesized as one of the reasons is because they've had their whole long stretch to have their potassium go up. And sometimes people even measure the pre-dialysis potassium in the 6s or 7s. And then then the reason I say don't use a 0K dialysate. 0K dialysates are probably not safe at all.
Even 1Ks.
Right.
You
got to remember, if somebody comes in with a K of 9,
right,
dialyzing them against a K of 3 or 4 is going to be okay.
Right.
You got a huge gradient there.
Right.
So you got to be careful, because the good news is, things are getting better because I'm removing K, and then you DKDT them too fast, and there's an arrhythmia. Right. So I want to just caution people that I think one of the big causes of the unexplained death in dialysis patients on Monday and Tuesday is not K, it's DKDT.
Right.
You can't, if it broke slow, don't fix it fast.
Right.
And these all broke slow. And that's nephrology.
Yeah.
It's like hyponatremia.
Exactly.
It broke slow.
Correct it slow.
Correct it slow. And this same thing for this. Okay.
And that one even more so, because that one is so electrical, and so many cells, especially the heart, care about it.
Right.
And
exactly. So this is another table, couple tables from the book. It's just my treatment of hyperkalemia. And again, it's just what I've outlined. Protect the heart, and then everything else. These are just the details that you can read in the chapter or read here. But basically the principles are the last slide. Okay, so now I want to end today by coming back to one of my favorite things in the whole world that, again, is only my favorite. A lot of people have forgotten about it. But there was a guy named Izzy Edelman. I mean, Izzy
you gotta
Edelman.
love Izzy Edelman. Only thing more Jewish than that is Rabbi Izzy Edelman.
I mean, when he comes from, I think he came from a family of rabbis.
I believe it.
But anyway, first of all, just saying Izzy Edelman makes me think I'm going to visit my uncle.
It's awesome.
Okay, so Izzy Edelman was a genius, and he was also he was actually the mentor for Bernard Rassier, whose group in Switzerland cloned ENaC. So the apple doesn't fall far from the tree. The ENaC doesn't fall far from the Izzy, because Edelman trained Rassier, and Edelman was interested in sodium. So the Edelman equation is really what we talked about a little bit, alluded to it with the tonicity talk. But this paper from JCI in 1958, I don't care what kind of nephrologist you are, this is a necessary part of every nephrologist library. If you're going to have one paper from the 1950s, this JCI paper is the one. This is the one that everything is based on. And look at the name of this paper.
Interrelations.
I mean, the title is longer than most papers. Interrelations between serum sodium concentration, serum osmolarity, and total exchangeable sodium, total exchangeable potassium, and total body water. So here's
That is totally the
that's
best
fantastic.
title.
That's a great title. Now here's probably the paper is excellent, and I can't go through it. It's not a journal club, but what I've circled here is the Edelman equation.
Okay.
And what they did is came up with what the plasma sodium concentration should be in terms of the total body exchangeable sodium and exchangeable potassium. Now notice here, what a lot of people forget is they think that if someone's hyponatremic, they sort of think, well, okay, taking away water is a good idea. Good idea. That's right. We talked about that. And some people will give sodium because they think, well, that's related. But do you know that potassium is related? It is.
Right.
The Edelman equation tells you that. So let me show you how in a fantastic teaching case that I think we'll end here with. So here's the Edelman equation. It's been simplified. The serum sodium concentration is the ratio of the sum of the exchangeable sodium and potassium. And this underscores the fact that tonicity is a total body thing.
Right.
Okay? Sodium is an ECF thing. Potassium is an ICF thing. But look, you need them both. And so it makes good sense that the exchangeable solutes in the entire body
Cares about what the two major kind.
Exactly. So the compartments are joined.
Right.
And then divided by total body water. And
That's awesome.
It's awesome. So let me show you a case that illustrates, because somebody said, well, but yeah, Dr. Segal,
Well,
but why
right.
should I care? Here's why you should care. And I'll tell you, this is spectacular and profound. Here's a real case. It's a 59-year-old woman who is an executive assistant. She's the executive secretary for this happened at Yale. It's an executive secretary for somebody who was one of the higher ups in the Yale administration. So a very competent person, okay? She's brought to the ED for altered mental status and inability to move, okay? And she was the only relevant history, she's got a history of hypertension, was started on a thiazide 3 to 4 weeks ago, and is a woman. And we talked about how women can have exaggerated responses, thiazides. So she weighs 72, normal vital signs, clinically euvolemic, obtunded. I mean, the family's saying we don't know her.
Right.
I mean, this is a sharp woman on Friday. This is a Sunday. She's sharp as a tack on Thursday, Friday, and on Sunday she's a
Decompensates.
mess. Look at the numbers, Craig.
Oof.
Okay, this would stimulate most nephrology consults. This is the lowest. I've seen 2 patients with the sodium concentration of 96.
Like 110 is the lowest I've seen.
Yeah, so this 96. This double-digit hyponatremia.
That is insane.
And look at the potassium. Okay? Now, my equation predicts this lady needs 962 millimoles of K, and there's a reason for that. I wanted to point that out. So the summary is you've got double-digit hyponatremia and severe hypokalemia. So, of course, why does she have altered mental status? Well, the inability to move is the K. The altered mental status is her brain is swollen to beat the band, okay? How should the patient be managed? Now, this is a very dicey case.
This is a dicey case.
Yeah, and if you don't know the Edelman, here's one of the statements I'm going to make. If you try to fix this woman and you don't know the Edelman equation, you're going to hurt her. Let's see what happened. So what happened is this. So she's got euvolemic hyponatremia. Her major problem is a decreased exchangeable K because of her diuretic. And so she's got this, she might have had exaggerated thirst response because that's what happens to women. An Israeli study showed that in the 80s. And she's got extreme hyponatremia, kalemia. The Edelman equation shows the perfect storm, that she's got such a low this and such a high that with, only, some this, she's very hyponatremic. Edelman would suggest initial treatment mostly be giving K. But how much? So this is a woman who the initial treatment for this 96 millimolar hyponatremia is not going to be
her
sodium.
ICF. Focus on the ICF.
Focus on the solute missing from the ICF. So here's what happened. Now, of course, you stop the thiazide.
Right.
Use the Edelman equation to calculate that the patient should be given 144, not the 400 she was given, 144 millimoles of K, orally or intravenously. And that would increase her sodium concentration from 96 to 100. That's safe. All you want to do is bring her slowly up to something that's not as bad as 96. Right. So this is a small step in the right direction.
Because you're pulling water. You're managing tonicity by treating her ICF's tonicity solute
deficit.
Yeah.
So unfortunately, they gave her 400 of K, and 400 of K.
Shot her up to 1. Yep.
And she actually shot up to 111.
Wow.
And guess what happened when she went from 96 to 111 less than 24 hours?
CPM.
She got the asthmatic demyelination
Oh,
syndrome.
yeah.
And it was a classic presentation. She looked like a rose for days. The day before the discharge. Everything, nothing, it couldn't be better. Everything's great. But this is how it happens. I've been unfortunate enough in my career to see asthmatic demyelination syndrome twice. Once when I was a medical student on OBGYN and once in Vermont. Those people often die.
Oh, yeah.
And they're left in a
Devastated.
They're left in a locked-in state. Now, this lady, and the classic story is this: they look fantastic,
Right.
and then the next day they're locked in.
Right.
This was what happened. She was set for discharge home, and then was unable to talk or walk or anything. And that's because they gave her a little saline and they gave her 400. And I'm not saying it was mismanagement at all.
Right.
This case is ridiculously difficult.
Challenging. I mean, this lady's...
But you can't, this is a case that says if you thought you could fly without Edelman,
Right.
you can't.
No.
You can't. And this loops in. So I wanted to end by looping in our hyponatremia talk and tonicity to our hypokalemia. And Edelman did it.
Right.
Edelman did it in 58.
Right.
And then he celebrated with a nice piece of fish. So what would have happened if you would have just gone by my equation? My equation gives you the right number, but look what would have happened. 123. She would have been terrible. So the bottom line, what happened to this lady is she survived, which is good. She went to a great rehab facility in Connecticut, and she did better.
Yeah.
But this is why it happened, and this is why. So flying without Edelman. This is a woman who was perfectly fine last week, was put on a thiazide. He kicks in, she gets this hyponatremia, and he loses all this K from the thiazide.
Right.
And without Edelman, she sunk.
Right.
And this is a very, this is not.
It's a great case to show you that giving potassium supplementation will change the sodium concentration.
Because what happens, she's so
You're
K
changing
depleted.
the free water.
She's so K depleted that when you give her the extracellular K, it goes into her cell.
Yep.
And what comes out is sodium.
Right.
And that will change the ECF sodium concentration. So potassium, so the question is, I'm going to change your sodium without even giving you any sodium. I'm doing it by giving you potassium. And somebody says, you can't do that. Edelman says you can.
And you're also bringing water into the cell because you're changing the tonicity of the intracellular space.
Well, you're changing the tonicity of the body.
Right.
Okay, you all remember, in the steady state, you've already changed it both. So this woman did poorly, but it's not, so our discussion is not purely academic. You know, when I bring up Edelman, 1958 JCI, that's the signal for everybody to go to sleep. Oh, he's gotten to Edelman 1958. My God, we can go to sleep now. No, this case could not be done without thinking of the Edelman. Okay, and so here's what you do. The right treatment for this lady is 144 millimoles of K only, and you could do it orally, because you could do it. You can do it over some time orally. Or if she's not awake, you could do it IV, and then maybe a small amount of saline, and then monitor her, because when thiazide wears off, she's going to also have an aquaresis. So this is a case that requires the ICU.
Oh yeah. Once you stop that, this is one where you're giving water. This is like Q2 hours electrolytes.
This is, and keeping a careful eye on urine output and everything.
Yeah.
And then the good news here's the good news, and it would have worked in here. If they would have realized when she went from 96 to 111, that was too much. And this was in the days before it was really well understood how fast you could go. Because the old days, when I came to Vermont, somebody with a 96 neuro would tell you she's going to seize unless you get it up to 120.
Right.
Yeah, not anymore. The good news about overcorrection, as we mentioned before, the goal of therapy in severe hyponatremia is to correct them 4 to 6 a day, no more than 8 a day, really. And if somebody in double digits, 4 is enough. That's why I went from 96 to 100.
Right.
4 is enough. If you overcorrect and she goes faster than you want, if you get in there with D5W, which is essentially water,
just add water.
It will lower this. It's now been shown for years now, since the days of relowering, overcorrecting is not terrible. It's going to happen.
Right.
Overcorrecting is not the thing to avoid at all costs. It's knowing if it happens what to do.
Right.
Okay. And what to do is give water and relower it. Right. And it turns out that I'm not aware of a single case of an overcorrected sodium concentration where they relowered it promptly with water who ever had osmotic demyelination syndrome. So that's what I want to say. So potassium homeostasis is the end. We have insulin that we talked about. We have the feedback system with aldosterone, and we have the gut caluriretic signaling pathway. I just want to end by showing you what the data on the feed forward. So here's the classic feedback, and here's the feed forward. It's somehow, when you eat, potassium goes up and aldo gets stimulated and the kidney listens. The feed forward is two things now. Not only does K go up, but there's some sort of a reaction in the hepatoportal and gut syndrome that somehow sends a signal to the kidney. And again, it's all question marks. But here's what happens. Here's the paper. Rapid dephosphorylation of the thiazide-sensitive co-transporter in response to oral potassium intake in mice. I'm not going to go through the data. Here's the paper, and here's the plots, and the data. You can look at that. You can stare at that. But what it shows is basically when they gave the mice the potassium not gastrically, this didn't happen.
Interesting.
So to get this dephosphorylation to happen, the K had to hit the stomach.
It's important. The stomach is an important part of the feedback system.
I've heard it's part of the body.
I heard that.
So again, dephosphorylation, and here's another thing that was very important. The second finding, not only it had to be oral, and oral loading of K didn't depend on aldo. So this is an aldo-independent response. And why shouldn't it be? You're dephosphorylating a protein. You don't need aldo. So aldo is listening to the serum K, and that's the feedback system in the mineralocorticoid. And this oral thing, this feed-forward system, is independent of aldo and just basically telling the kidney. It's like yelling down to the, like we got company. If you want to, if too many people show, if you had a dinner party for 4 and everybody brought another person, okay, family hold back. We got 8 here.
I know.
So that's what this is. And so again, to show you the model, and here's the model essentially, that in high K, and I'll just make it all that. In high K, you're going to depolarize. Calcium is going to go up in the zona glomerulosa. Aldosterone gets secreted, and there's caluresis. In the DCT, you've got this going on. And in low K, you've got just these opposite things happening. But, here you get increased NKCC activity. It stays phosphorylated by the Wnt kinase. Here, when you have high K, NCC by the feed-forward pathway is dephosphorylated, and you get caluresis. But you get the thing you want. You get a high K, you get increased caluresis. You get a low K, you get decreased caluresis.
It's awesome, man. It's independent system from the aldo process. That's so interesting.
So what you came in with today is having a good understanding of RAS and aldo. But what you learned was 2 things. You learned, first of all, about the aldosterone paradox.
Correct.
Okay, about how they use the same
There's
hormone, but they don't step
for
on their
volume and potassium management.
Exactly. And now you've learned, even though you knew about aldo, even though you knew about K and the feedback system, you got this. And with armed with this, you got it all. And what does it do? It's affecting transporters, just like you'd want it to. So again, this is just another cartoon. This is from Dave Ellison and Andy Turker. His group in a nice paper in Cell Metabolism where they really outline, what's going on. And you see again, high K depolarized, low K hyperpolarized, toward EK, and that's what happens. So this is just the final figure to really look at everything. This is an analysis of that paper where you got a K load and if there's no insulin, you're going to be in trouble. Okay, and if there's insulin, but you don't have aldosterone working, you might be in trouble. Here's what you really want. You want to eat a meal that has carbohydrates and potassium, and you want to stimulate your insulin, get that transfer. Then you want to have your aldosterone system working, and then all of a sudden, sneaking in here is the gut factor with a question mark, and that's the thing. So this is to me is cutting edge K homeostasis.
The gut factor is dephosphorylation.
Yeah. So the only thing in this talk that really wasn't in my chapter was this gut factor. And so that's,
but it's brand new.
So the chapter updated with the gut factor is pretty close to where we are. And based on last week's ASN, I listened to every potassium talk. I was listening to see if there was anything newer than that. And the bad news and the good news is there wasn't. Okay. So this again is my favorite figure. Again, I made the figure, so I'm going to like it. anybody's interested in the chapter. But I think, Craig, that we've done 3 talks together.
Yeah.
And even though we've done 3 talks, they're not 3 different talks.
Right.
The number of times we've had to invoke acid-base today and sodium and tonicity today that's what I'm saying. This talk is great.
I was saying that's the trifecta. This is the perfect 3 talks to go together.
Yeah, and these are difficult concepts for people. And this talk sort of brings it home by showing you, if you thought that you could talk about potassium without talking about acid base or Edelman,
right.
Well, this is what you've got here.
That's
And it's
awesome.
practical at the bedside. You carry that picture in your mind of the collecting duct, and you got to even take Edelman with you. If you get a case next week and somebody calls you up and they go, Craig, what are we going to do? I got a sodium of 99 here. You're going to know.
That's right.
And so there was
the potassium's 1.8.
So I'll tell you one last final
right.
funny story is I always felt once a program director for somebody, always a program director. So even when my fellows graduated and became attendings, one great thing for me is they would scatter around the country or go across the lake.
Yeah.
And yet I always told them, remember, I'm always your program director, as long as I'm alive. Keep me alive. And I said, they would be a little bit scared or a little intimidated or apprehensive about what happens when I see something I can't handle. And they said, well, what did you do during a fellow? Well, we called you.
Right.
I go, well, you
give a call.
You think my phone's not going to work because you're not a fellow anymore?
Right.
So give a call. And what's happened is I have received over the years some great cases of former fellows. I remember Tobin calling me once. And somebody else called me with a very severe case of hyponatremia where we really had to use Edelman. And so it's practical.
Wow.
And so I'm hoping that people will watch these talks, get interested in nephrology. That's what we're hoping.
That's the goal.
And get interested. But see that really, even though we've given 3 talks, and they weren't short, but 3 talks, but that they're all, we keep saying many of the same things.
Right.
Goldilocks is in every talk.
That is it. I mean, it's been fantastic, Alan. You've done an amazing job, putting these topics together for us. And this one, which is really, like I said, it completes the trifecta because it allows you to really pull it all together. And I want to thank you so much for coming here to do this. And we will talk about dialysis. We have a lot of things to talk about.
I got to tell you, this may not sound great for me, but the fact that this is the most fun that I've had in years,
right?
It may say something about my life, but really, getting together with you and talking to you and having this kind of interplay when we're talking about this,
right?
And you've got the country doctor guy,
and the academic guy,
and really, if I were watching this,
well, I
would
ask
be
the
in heaven.
questions, right? Because I'm asking the questions.
Right.
All my friends
Right.
are wanting to ask.
Yeah,
so
and so we tackled some things that people, and we tried to demystify.
And
let's continue the theme of demystifying.
I love that. That's
Okay.
going to be our new title.
All
Alan,
right, Craig.
thank you so
You're
much.
welcome.
And
Welcome.
we will talk to you soon.
College.
That's it, baby.